Hello, friends. Today our space journey will take you to one of the most mysterious places in the universe, a black hole. On our channel we with you have already tried to understand the question of the nature of black holes. But in this video, we want to explore the paradox of information disappearing in a black hole. What is the nature of this problem? Where to look for possible solutions? What surprised Stephen Hawking, the entire scientific community in their report? And how will new knowledge about moleholes affect our view of the universe? Let's find out. The universe is an amazing and strange place filled with unexplained phenomena. One such phenomenon, the black hole information paradox, seems to violate a fundamental physical law. Stephen Hawking's work has influenced many fields, including cosmology, and in particular, quantum gravity and black holes. He was the first to point out that black holes behave in a way that puts two fundamental theories, relativity and quantum mechanics, in conflict with each other. This paradox has puzzled scientists for half a century and has led some to question the fundamental laws of physics. An early report by Professor Hawking suggests that the event horizon of a black hole is considered to be the final frontier. Once outside of it, nothing can leave a black hole, not even light. But is this information per se relevant? Will it be lost forever in a black hole like everything else? First of all, we should realize that the information paradox of black holes is not related to the way we are used to perceive information. When we think of the words printed in a book, the number of bits and bytes in a computer file, or the configurations and quantum properties that make up a system of particles, we think of information as the complete set of everything needed to recreate anything from scratch. However, this traditional definition of information is not a direct physical property that can be measured or calculated, as, for example, can be done with temperature. Fortunately for us, there is a physical property that we can define as equivalent to information, entropy. Instead of thinking of entropy as a measure of disorder, they should be thought of as the missing information needed to define a particular microstate of some system. To explain why most scientists think there is some kind of paradox, a few comments are in order. In school, we learn that electromagnetic waves come in different frequencies. If you start with the lowest frequencies, that would be radio waves. Then, if you increase the frequency, it's infrared. Then, if you zoom in even further, we get waves from the visible light spectrum. Next, beyond the visible spectrum would be ultraviolet radiation. Next come X-rays and even farther away gamma rays. If we put radiation sources at some distance from some massive object and follow the light it emits at a large distance from the center of gravity, we will see what is called infrared shift. That is, the observed frequency of radiation far from the gravitating body will be somewhat lower than the radiated frequency in its vicinity. The reason for this is very simple. The fact is that the energy of photons of electromagnetic waves is directly proportional to their frequency. A photon of infrared light has less energy than a photon of ultraviolet light. The electromagnetic wave, as it overcomes gravitational attraction, does work, consequently loses energy, and its frequency decreases. For a body like Earth, this effect is quite weak compared to some star. If the latter has a small size and a large mass, for example, if it is a neutron star, the infrared shift can be quite large. In turn, for a black hole this phenomenon reaches an extremum in the following sense. The specificity of a black hole is that it has a so-called event horizon, such a surface from which any radiation undergoes an infinite infrared shift. That is, if the radiation source is right on the horizon, you see the field it produces as not changing over time. No radiation. The horizon is precisely the surface from the limits of which light cannot escape. Black holes are arranged in such a way that they produce exclusively stationary fields, even if they rotate on their axis. Assuming their center of mass is at rest, The gravitational and electromagnetic fields they create will not change in time. This statement is called the black hole hairlessness theorem. In 1992, the principle of additionality was proposed, according to which information is in some sense both inside and outside without violating quantum theory. The conjecture was developed by one of the originators of string theory, Leonard Susskind, and his young colleagues. Specifically, observers who remain outside the black hole see information accumulate on the horizon and then fly away with the Hawking radiation. Observers falling into a black hole see the information inside. Since these two classes of observers cannot communicate, the paradox does not arise at all. Many solutions to this paradox have been proposed. The Brandmauer theory, in which all information is burned up before it enters a black hole, to the fuzz-ball theory, which states that black holes have no clear boundaries. But most of these proposals required changes to the laws of quantum mechanics or Einstein's theories of gravity, the two pillars of modern physics. Unlike other theories, quantum Hare theory unites the general theory of relativity with quantum mechanics by means of new mathematical expressions. Its name refers to a hypothesis of classical physics, that black holes can be considered as surprisingly simple objects defined only by mass and rotation speed. This theory, devoid of black hole properties, was called the no-Hare theorem in the 70s. In 1975, Hawking allowed that black holes would gradually disappear due to quantum effects at their event horizon, emitting energy in the form of radiation. This hypothesis, meanwhile, has posed a problem for theorists. Its essence is that evaporation of black holes and birth of radiation implies that almost all information about quantum state of particles, absorbed by black hole except for their mass, charge and speed of rotation, will be irretrievably lost. That contradicts laws of quantum physics. However, Hawking wrote, this is not quite the case. According to the scientist, part of the information absorbed by black holes will leak outward in the form of photons with almost zero energy, standing in place of the evaporating black hole. This phenomenon he called soft hair. Thus, information will be stored at the boundary of this region, called the event horizon. Photons will act as information carriers. They will record the properties of the particles eaten by the black hole. Black holes are not eternal prisons, as previously thought. Hawking said in 2015. If you feel like you've fallen into a black hole, don't give up. There's a way out. However, according to his theory, there will be no return to our world, to the starting point. The subject will be in some other, alternative space. Scientists at the University of Sussex, England, believe they may have solved Hawking's famous paradox. Researchers claim that black holes actually have properties called quantum hair, The Guardian reports. For many years, it was believed that solving Stephen Hawking's black hole paradox would force a reformulation of either quantum mechanics or the general theory of relativity. But we came to the conclusion that this was not necessary, says Xavier Calmet of the University of Sussex. When matter enters a black hole, it should leave a faint trace in its gravitational field. This trace should be considered quantum hair. They are the ones that provide the mechanism for preserving information during the collapse of a black hole. According to this theory, two black holes with the same masses and radii, but with different internal composition, will have very subtle differences in their gravitational fields. Our theory explains how information can be stored, and there is no need to make radical changes to the understanding of physical laws, Calmet says. There is no way to test this theory yet, because the gravitational fluctuations of black holes would be too small to be measured. However, all of the above was based on some qualitative reasoning. All of them require a formal computational proof. These computational proofs of the paradox are formulated with such a low degree of rigor and under such a number of crude assumptions that it can be refuted with the same degree of rigor. Another thing is that many details of different processes that occur in the presence of black holes remain unclear. And for that part of the scientific community which considers that there are paradoxes, its decision is a guiding star in knowledge of the nature of black holes. It is so often the case in science that there are different points of view regarding an as yet poorly understood subject, says Emil Akhmedov, PhD, a physicist and mathematician. Over the past few years, theoretical physicists have identified key points overlooked in Hawking's original calculations. Calculations completed in 2019 have finally given scientists an idea of how this information might be preserved. Plus, learning exactly how quantum computing works can present new insights into what the theory of quantum gravity is all about. In 2021, researchers Kanado Guro, Thomas Hartman and Amir Hossein Tidini discovered something else interesting. Mole holes or wormholes can connect different separate regions of the universe. This may shed light on what happens to the information about matter absorbed by black holes after all. A mole hole or wormhole is a hypothetical structure that allows one to pass through space-time and end up elsewhere in the universe. It is believed that wormholes exist precisely because of the gravitational influence of black holes. Eventually, the black hole will completely vaporize, as will any information about its absorbed contents. But this contradicts the fundamental dictum of quantum physics: information cannot disappear from the universe. The researchers were able to study how black holes mimic wormholes, providing a pathway for information evacuation. It should be understood that this is not a wormhole in the real world, but a way of mathematically calculating the entropy of radiation. Thus, the wormhole connects the inside of the black hole and the radiation from the outside like a bridge. If the quantum Hare theorem or the black hole wormhole connection holds up to scrutiny, it could be the first step in unifying Einstein's general theory of relativity with quantum mechanics. This problem is another unsolved problem in physics. Despite the increased number of questions and the desire to understand how the universe came into being and how it works, gravity will have to be considered as a quantum phenomenon. All because it is impossible to understand what happens to information without the theory of quantum gravity. Which means we'll be waiting for further discoveries.